All right, everybody. So I wanted to create a short video for you that shows you how to combine trig functions, particularly as they pertain to solutions of differential equations. Because for right now, what we've been finding is that for complex roots to our auxiliary equation or our characteristic equation, we tend to get something that looks like C1 and then a cosine of maybe a BT here, and then like a C2 sine of BT. And oftentimes, in the textbook or wall map, you might be asked, what is the amplitude, and what is like the period of this graph. And it's not very easy to tell, specifically because these C1s and C2s are usually very different. For instance, if we have as an analogy, maybe on the right side, a solution maybe we get is e to the t, and then maybe we have like a 4 cosine of 5t, and then plus 3 sine of 5t or something like this. Okay. And so, it's not really obvious. Now, we've seen that when we look at graphs like this, depending on what's happening, the graph kind of does something like this, and maybe it's underdamped, and so it just gets really big, or maybe it's overdamped and it just goes like this, and then it dies off. And so the question is, what's kind of going on with this graph, and so what we can do is we can actually use some very clever, sneaky tricks to combine this into a single trig function. And the way that we do this is, the first thing that I'm going to do is it's very clever. I'm going to build a triangle. I'm going to build myself a right triangle. And I'm going to label, this side C1, and I'm going to label this side C2. And then what am I going to label? What am I going to label this side? I'm going to call this side just something random A, and I'm going to give it some angle theta. Okay, so I've built a triangle, a right triangle for no reason, that has side length C1, C2, and a hypotenuse of A. And I'm going to just kind of write down some things that we immediately notice with this random triangle that I built. First and foremost, that cosine of theta here is equal to C1 over A. We notice that sine of theta is equal to C2 over A. And we also notice that A is equal to the square root of C1 squared plus C2 squared. And so what does this allow me to do? What this allows me to do is this allows me to take this expression, allows me to take that expression right there, and I'm going to rewrite it using all of this. I'm going to rewrite it as, well, let's see, we had C1, and then we had, but wait, what does C1 equal? C1 is equal to A times cosine of theta, and then I still have my cosine of BT. And then what does C2 equal now? Well, C2 is going to equal A times sine of theta, and then we have times sine of BT. And so this, right, we can factor out an A. We could factor out an A and get A times everything on the inside. But cosine theta, cosine of BT, and sine theta, sine of BT, that is a trig identity, actually. And it just actually becomes A times cosine. A times cosine of what? Well, it turns out that A of cosine of BT minus theta. So we can, it's a trig identity for it is a difference identity for the cosine function. And what depends kind of like, what the values are, whether or not this ends up being a plus or a minus. But I'm just going to write it in this form. And so, you know, and so like, what does this look like with the problem on the right? So what this means is basically I'm going to construct myself a little right triangle on the right over here. And I'm going to label this side 4. I'm going to label this side 3. Hopefully with not too much thinking, this means our missing side here is going to be 5. That's our A. We have some angle theta. Don't know what theta is yet. But what we know is that we can then go ahead and take the stuff that's inside this parentheses and write this as, well, let's see, what's our coefficient become? Well, according to the little manipulation that we did over here, the coefficient is just going to become, we're going to get 5 cosine of theta times cosine of 5t, and then plus 5 sine theta, and then sine of 5t. And this condenses very nicely into just 5 cosine of 5t minus theta. And how do you figure out what theta is? Well, you can use, you know, trig inverse of anything. You could do like sine inverse of 3/5, say, and you can plug this into a calculator and figure out what it is. And so well, maybe I'll just do that really quick on my calculator. So this is going to take a moment, but if I pull out my calculator and I do sine inverse of 3/5, I get roughly like 37 degrees. So this is roughly 5 cosine of 5t minus 37 degrees. Maybe I should be in radians. So radians. This is 0.64 radians. 0.64 radians. Okay, something like this. And you might be wondering, okay, well, why are we doing this, right? Why are we doing this? It's a very, very natural question. Okay, so the first thing is that unlike what we started with over here, our solution now looks like e to the t times 5 cosine of 5t minus 0.64. So what do we get from this new solution that we've basically constructed? We get a couple things. The first thing is that we can figure out the period of this graph, right? 2 pi over 5 is how we can get the period, right? How long is it going to take to start repeating itself? We can get a phase shift or a horizontal shift of the cosine graph. We can see that the amplitude when t is 0 is going to start up at positive 5. That's where our graph would start. Okay, it'd be up at positive 5. We can also see that since we have a positive e to the t term here, that we're going to be taking 5 and multiplying it by something that's going to grow, which means that our graph is going to start up at 5, and then it's going to get bigger and bigger and bigger and bigger. And right, we get a lot of useful information for analyzing like what's happening to our function, whereas if we look at the original version of our solution over here, it may not be so clear. Like maybe you have some ideas that, you know, the e to the t term over here is going to cause things to grow because this is a positive 4 and a positive 3. And maybe you have the idea that this is going to be a period of 2 pi over 5 or something. I'm looking there, but this is kind of a way to write it as one single trig function, which is it's super slick. It's really nice. And so you can use this to rewrite solutions in this form. Now, I want to caution one thing, which is that if you rewrite your solution in this form, while you do get some good information like what is your starting amplitude, what's your period, and maybe a phase shift if you're asked it, you need to remember that 3 sine of 5t was once upon a time, you know, it is a component of this new solution, right? That hidden inside of our new solution at the bottom here is this 3 sine of 5t. And that's going to be important because later on when we're going to end up solving non-homogeneous differential equations. And the idea being that if you solve for what's called the particular solution, if I were to get that I think the solution is sine of 5t, you would have to remember that, well, that's already been accounted for in the homogeneous solution, and so we need to slap on a t in front of this thing for it to work. Whereas, if you were just presented that the solution to your differential equation, the solution to your homogeneous differential equation was what I have circled here in pink, you may not realize that like sine is part of that, and you might improperly state that your particular solution is sine of 5t, when in reality this equation is secretly was made from sine of 5t or something like that. Or I guess since they all have an e to the t multiplied by them, there would need to be like an e to the t here already as well. But anyways, that's kind of like the point. So this is kind of a very short, just rough video. It's just using some algebraic manipulation to write your solutions. Instead of as two separate trig functions, you can combine them into one single trig function for getting some useful information from it.